This is a lesson on an introduction to vectors. This lesson will introduce some very basic ideas about vectors. Other lessons will introduce more advanced ideas. Why do we even study vectors? In physics, we will deal with several physical quantities that behave as vectors, and when we want to deal with those quantities mathematically, vectors are the way to go. A few of the quantities that behave as vectors are displacement. That's a way of describing where an object has moved to from where it began. Velocity is how an object is moving right now, how fast and in what direction. Acceleration describes how the velocity of an object might be changing. A force is a push or pull. These are the things that cause the motion of objects to change. Some other quantities that we'll learn more about later are momentum and electric and magnetic fields. We won't describe these now, but we will use them later. So, just what is a vector? For us, there will be three properties of vectors, and then we'll have some notation for vectors that we'll look at in this lesson. The first property is that vectors have a direction. They point somewhere. Most of the time, we'll use an XY coordinate system that you know and love from your math classes, and we'll have the vectors point in some direction on that XY grid. The XY system is only two-dimensional though, and at times we might need a third dimension. In that case, we'll add a third axis and call it an XYZ coordinate system. Every once in a while, we'll also describe some motion on the surface of the Earth. When we do that, we'll have the vectors point in various combinations of north, south, east, and west, and in between. The second crucial property of vectors is that they have a size, which we call the magnitude. Now, the word magnitude has many different meanings in different contexts, but when we're talking about vectors, we'll always use magnitude to mean the size of the vector. Sometimes that size is a length, if we're talking about the position or the displacement of an object, but for a velocity vector, the magnitude of the vector, its size, will actually be the speed of the object. We often draw arrows to represent vectors, and when we do, it is sometimes useful to let the length of the arrow represent the magnitude of the vector. We do this even when the vector represents something other than length. So if the vector represents a velocity, the arrow we draw for that velocity will be longer the faster the object is moving. The top arrow here might represent a slow velocity, and the bottom one a faster velocity. Now just a little terminology about vectors. Over on the right, where the arrow tip is drawn, is what we call the head of the vector. On the left is what we call the tail of the vector. When I actually draw these things, I tend to draw from the tail to the head, so I often call the tail the start of the vector, and the head is what I call the end of the vector. Those are things that I tend to use. They're not official terms, but if you hear me say the start and the end, that's what I'll be talking about. I've only mentioned two of the properties of vectors. First, that they have a direction, and second, they have a magnitude. The other property of vectors is that they add in a particular way. Watch this animation that's going to show up here to see how vectors add. When we add two vectors, we draw the first vector from tail to head, then we draw the second vector so its tail begins where the head of the first vector is. Then the sum of the two vectors starts at the tail of the first vector, way over on the left, and ends at the head of the second vector, way over on the right. It's important that you perform this head-to-tail addition process correctly. Here's another way to picture the process. Start by drawing the first vector with its correct length and in its correct direction. Then at the head of the first vector, you begin drawing the second vector with its correct length and its correct direction. The sum of the two vectors will then point from the start of the first vector to the end of the second vector, from the tail of the first to the head of the second. Let's look at an important point about adding vectors. First, the correct head-to-tail addition method. These are vectors that point in different directions now. That gives vector 1 plus vector 2, the sum of the two vectors. Now, let me show you an incorrect way to add vectors. Did you see what I did wrong here? I joined the two vectors tail to tail. Now, these are the same two vectors that I added together over on the left, but there's no way I'm going to be able to draw the correct sum of those two vectors from what I've got here. In fact, I can get two different answers from this drawing, the one on the right, that is. The first one points from the head of vector 1 to the head of vector 2. And this vector is actually vector 2 minus vector 1. We'll learn why this is the case in a later lesson. Now, I can also draw a vector in the opposite direction, from the head of vector 2 to the head of vector 1. This vector happens to be vector 1 minus vector 2, and again, we'll learn why this is the case in a later lesson. Don't try to add vectors the way it's done on the right. The way on the left is the correct way to do it. A bit more with the addition of vectors now, and this will show us the usual way that vector addition is described. We'll begin with a starting point where we'll begin drawing the first vector. We'll call the first vector vector A, and it points from the starting point to the direction it's supposed to point. We draw vector B starting at the head of A. Now, before I draw the sum of these two vectors, I'm going to go back to the starting point and first draw vector B going out from the starting point. Oh, by the way, that's the ending point over there. First, I'll draw vector B starting from that starting point. And then I draw vector A starting from the head of B. Notice that I've ended up at the same place I did when I added them in the other order. Notice also that we now have the figure of a parallelogram. Vector A and a copy, and vector B and a copy, or vector A first, vector B second, vector B first, vector A second. They combine to form a parallelogram. Now we draw the diagonal of the parallelogram, beginning at the starting point and ending at the ending point. That diagonal is the sum of the two vectors. The way that the two vectors add is usually called the parallelogram rule of addition, and from this figure you can see why. You can also see something else from this figure. Along the top, I drew vector A first and vector B second. Along the bottom, I drew vector B first and vector A second. The result was the same. Vector A plus vector B equals vector B plus vector A. Since the order of addition doesn't matter, we can say that vector addition is commutative. That may not seem like such a big deal, but if you go far enough with vectors, you may get to the point where you find some operations with vectors don't act the same as operations with the ordinary numbers you've dealt with before. And in fact, there's one operation that when you do it in the reverse order, you get the negative of what you did in the other order. So won't that be fun? Okay, time to quiz yourself. Write down the properties of a vector. No fair peeking at the answers. Write them down. I'm going to pause here for a few seconds, but you should pause the playback so you can write out your answer. Ready? Okay, first property, a vector has a direction. It points towards some direction in space. Second property, a vector has magnitude. Third, vectors add according to the parallelogram rule. Did you get them all? Let's try another quiz. Get ready to pause this and write down your answers. Name two quantities that are vectors. No fair peeking. Pause the playback now and write down your answers. Ready? Okay, here are the quantities that behave as vectors, at least the ones I've given you. There are some other things as well. To finish this lesson, I'm going to show you just a few things about vector notation, how we indicate that something we write is a vector. When we're writing them down, we indicate vectors by writing an arrow above a letter. You can see some examples here. It doesn't matter whether you have half an arrow as you see above the A, B, and R, or a whole arrow as you see above the V. When you're writing them by hand, either one indicates that the quantity is a vector. The numbers you've been dealing with up until now are called scalars. When we write a scalar, we don't bother putting arrows on top of them. A little more with the notation here. As you begin to work with vectors, you have to be careful how you write things. When we write a letter with an arrow above it, we mean the vector. So this would be the vector A. That thing that has magnitude, direction, and adds according to the parallelogram rule. When we write just the letter, we mean the magnitude of the vector. By the way, the magnitude of a vector is a scalar. The only information that letter contains is the magnitude and whatever units happen to be associated with the quantity. There are some other notations for the magnitude of a vector. Sometimes you'll see the vector with the arrow symbol on top wrapped inside absolute value bars, and sometimes inside double absolute value bars. I don't use those notations in my classes, but you might see them in other classes. All the notations mean the magnitude of the vector. One last little bit for this lesson, unit vectors. You can see the properties of unit vectors here. They have direction, a length of 1, and no physical units, and they have a little caret on top of them like that. Most of the time we'll confine ourselves to the XYZ coordinate system, and usually just X and Y, and we'll use the unit vectors associated with those, which are written as I hat, J hat, and K hat. That's the way they look when they're typed. When we write them out, at least when I write them out, they're going to look a bit more crude than that, and that's the way my I hats, J hats, and K hats are going to look. That's it for this lesson. In future lessons, we'll look at more things that you can do with vectors.